Tonight, as you settle in and prepare for rest, let's journey not outward to distant stars, but downward into the mysterious realm that covers most of our home planet. The ocean, that vast blue expanse that hides more secrets than perhaps any other place on Earth. Maybe you've stood at its edge, felt its cool waters against your skin, or gazed out at a horizon where sea meets sky in perfect harmony. But tonight we'll venture far beyond the familiar shoreline and surface waves, descending into a world few humans have ever witnessed firsthand. As you relax, imagine the weight of the day slowly lifting from your shoulders, like a diver shedding ballast to begin a gentle descent. Let your breath find its natural rhythm, like the steady pulse of tides that have washed against Earth's shores for billions of years. There's nothing to do now but drift and discover as we explore the most enigmatic wilderness on our planet, the deep ocean. The ocean holds 95% of all living space on Earth, yet humans have explored less than 5% of its vast realms. It seems almost impossible in our age of satellites, supercomputers, and space travel, but our ocean depths remain more mysterious to us than the surface of Mars. There is something both humbling and wondrous in this thought, that our home planet still keeps so many secrets hidden beneath its shimmering surface. Water covers more than 70% of Earth's surface, creating an interconnected ocean that wraps around our world like a flowing, living blanket. If we could somehow drain away all this water, we would discover a landscape more alien and dramatic than any science fiction writer has imagined. Towering underwater mountains, valleys deeper than Mount Everest is tall, vast plains, smoking, chimneys and geological features with no counterpart on dry land. The average depth of the global ocean is about 12,000 feet, but in its deepest trenches it plunges to nearly 36,000 feet, a depth where the pressure exceeds 8 tons per square inch. These abyssal regions exist in a state of perpetual darkness. Sunlight, which sparkles so brilliantly on the ocean's surface, penetrates only about 600 feet into clear water. Beyond this twilight zone, the ocean becomes an endless night, unbroken by the rhythm of day that governs life above. Yet even in this darkness, life has found extraordinary ways to thrive, creating entire ecosystems unlike anything on the sunlit surface of our planet. When humans first began to wonder what might exist in the ocean depths, many believed nothing could survive in such hostile conditions. The great naturalist Edward Forbes proposed in the 19th century what became known as the azoic theory, the belief that life could not exist below about 1,800 feet. The crushing pressure, the total darkness, and the presumed scarcity of food, he reasoned, would create a lifeless desert beneath the waves. How beautifully wrong this assumption proved to be. Far from being empty, the deep ocean teems with life forms so diverse and strange they might well have evolved on another planet. Yet they share Earth's waters with us, existing in parallel with our sunlit world, following different rules and rhythms, adapting to conditions that would kill surface dwellers in moments. The first significant challenge to Forbes's theory came in 1860, when a telegraph cable was pulled up for repairs from more than 5,000 feet beneath the Mediterranean Sea. Clinging to the cable were several living creatures, proof that the deep was not barren after all. This discovery opened scientific eyes to a possibility that has only grown more fascinating with each passing decade, that the deep ocean might be home to an astonishing array of life, adapted to one of the most extreme environments on Earth. The true revelation came in 1872, when the HMS Challenger set sail on what would become the world's first dedicated oceanographic expedition. Over 3.5 years, the converted warship traveled nearly 70,000 nautical miles, sampling and dredging the deep ocean. The expedition collected and described over 4,000 previously unknown species, forever changing our understanding of life on Earth. What the Challenger scientists discovered was merely the first glimpse into an alien world. Today we know the deep ocean hosts countless species that exist nowhere else, from transparent shrimp and bioluminescent fish to living fossils like the coelacanth, a creature that was thought to have gone extinct with the dinosaurs until it was discovered alive in 1938 off the coast of South Africa. Each new deep-sea expedition reveals dozens or even hundreds of previously undiscovered species, suggesting that we have only begun to catalogue the diversity of life in the abyss. The deep sea begins beyond the continental shelf, where the shallow coastal waters drop away into the open ocean. This continental slope is like the edge of a vast underwater cliff, descending quickly into depths where light fades and pressure mounts. As you would sink past 600 feet, the last blue hints of sunlight would disappear, leaving only the faint glow of bioluminescent creatures to break the endless dark. Between 3,000 and 13,000 feet lies what oceanographers call the bathyal zone, a realm of increasing cold and pressure where temperatures hover just above freezing. Here, the diversity of life begins to change dramatically. Many familiar fish disappear, replaced by species with special adaptations for deep water living. Their eyes often grow larger to capture any faint traces of light, or in some cases disappear entirely in creatures that have evolved beyond the need for vision. Deeper still, between 13,000 and 20,000 feet, stretches the abyssal plain, one of the most extensive habitats on Earth, covering more than half the planet's surface. These vast underwater deserts are punctuated by seamounts, underwater mountains that rise thousands of feet from the seabed but never break the surface. An estimated 30,000 of these seamounts exist in the world's oceans, each one potentially hosting unique ecosystems adapted to its particular conditions. Below 20,000 feet begins the Hadal Zone, named after Hades, the ancient Greek realm of the dead. This fitting name describes the most extreme environment on our planet: deep ocean trenches where pressure exceeds 1,000 times that at the surface. Yet even here, in these crushing depths, life persists. During the 1951 Galathea expedition, scientists discovered thriving communities of animals living in the Philippine Trench, more than 33,000 feet below the waves. What makes these discoveries so remarkable is not just the extreme conditions these creatures endure, but how little we still know about them. New species are being discovered at such a rate that marine biologists estimate we have identified perhaps only 1/3 of all deep-sea species, and that may be an optimistic assessment. Some scientists believe we might have catalogued less than 10% of all life in the deep ocean. This ignorance isn't merely academic. The deep sea influences our world in ways we are only beginning to understand. Ocean currents regulate our climate, while deep-sea organisms play crucial roles in nutrient cycling and carbon sequestration. The mystery of the deep isn't just a frontier of exploration. It's a frontier of knowledge essential to understanding our own place on this blue planet. One of the most unexpected discoveries in deep-sea exploration came in 1977, when scientists piloting the submersible Alvin discovered something that would revolutionize our understanding of life on Earth. Near the Galapagos Islands, more than 8,000 feet beneath the surface, they found a series of hydrothermal vents, underwater geysers where superheated water, rich in minerals, pours from cracks in the ocean floor. What astounded the scientists wasn't just the vents themselves, but the rich communities of life surrounding them. Giant tube worms, some growing to 10 feet tall, clustered around the vents alongside unique species of crabs, mussels, and shrimp. These creatures weren't just surviving in the darkness. They were thriving in an environment completely independent of sunlight. Unlike virtually all other ecosystems on Earth, which ultimately depend on photosynthesis and the sun's energy, these deep-sea communities rely on chemosynthesis, a process where bacteria convert chemicals from the vent fluid into usable energy. The discovery of these black smoker communities fundamentally altered our conception of what conditions are necessary for life. It expanded our understanding of where life might exist, not just in Earth's oceans, but potentially on other worlds like Jupiter's moon Europa or Saturn's moon Enceladus, both thought to harbor vast subsurface oceans. The creatures that make their home in the deep have evolved extraordinary adaptations to survive in an environment that would kill surface dwellers in moments. Many deep-sea fish have soft, watery bodies with minimal skeletons, allowing them to withstand the enormous pressure. Some, like the barrel-eye fish, have transparent heads filled with fluid, through which they can rotate their tubular eyes to look upward for prey silhouetted against the faint glow from above. Other inhabitants of the deep use bioluminescence, the ability to produce light through chemical reactions, to navigate, hunt, or find mates in the darkness. By some estimates, more than 90% of creatures living in the open water of the deep ocean produce some form of light. This creates a twilight world where brief flashes, glowing lures, and pulsing patterns break the perfect blackness. The anglerfish, perhaps the most iconic deep-sea creature, dangles a glowing lure in front of its enormous fang-filled mouth to attract prey. The female anglerfish may be the size of a football, while the male is often no bigger than a fingernail. In some species, the tiny male permanently fuses to the female, becoming little more than a parasitic appendage that provides sperm when needed, a remarkable adaptation to the challenge of finding a mate in the vastness of the deep. Other deep-sea hunters have evolved more subtle strategies. The viperfish's enormous teeth are so large they wouldn't fit inside its mouth. Instead, they curve back along its face when its jaws are closed. The gulper eel can open its jaw so wide and stretch its stomach to such an extent that it can swallow prey larger than itself. The black swallower, despite being only about 10 inches long, can consume fish 3 times its size, its stomach expanding like a translucent balloon to accommodate its oversized meal. These adaptations might seem grotesque or alien through human eyes, but they represent beautiful solutions to the challenges of surviving in an environment unlike any other on Earth. The deep sea is a world where energy is scarce, encounters are rare, and efficiency is everything. Every bizarre feature serves a purpose, refined through millions of years of evolution to perfect life in perpetual darkness. Not all deep-sea creatures are predators, however. Many are scavengers, patiently waiting for the rare bounty of a dead whale or other large animal to sink from above. These whale falls create temporary oases in the food-poor abyss, supporting specialized communities that may feed on a single carcass for up to a century, cycling through distinct phases as different organisms consume various parts of the body. Others feed on what scientists poetically call marine snow, a gentle, constant drift of organic particles from surface waters. Dead plankton, fecal matter, mucus, and other debris slowly sink through the water column, providing a sparse but continuous food source. By the time this material reaches the deepest parts of the ocean, it may have been falling for weeks or months. The slow pace of life in the deep reflects this scarcity of energy. Many deep-sea creatures grow slowly, mature late, and live extraordinarily long lives compared to their shallow water relatives. The orange ruffy, a commercial fish found at depths of up to 6,000 feet, can live for more than 100 years. Certain deep-sea corals may be among the oldest living organisms on Earth, with some colonies estimated to be several thousand years old. This slow pace extends to the very movements of deep-sea creatures. Many conserve energy by remaining relatively stationary, waiting for food to come to them rather than actively hunting. When they do move, they often do so with deliberate efficiency, minimizing unnecessary expenditure in an environment where every calorie counts. The geography of the deep ocean is as varied and dramatic as any landscape on land, shaped by the same forces of plate tectonics that build mountains and create earthquakes. The ocean floor is divided by the mid-ocean ridge system, a continuous mountain range that stretches for more than 40,000 miles around the globe, making it the longest mountain range on Earth. Along this ridge, new oceanic crust forms as magma wells up from below and solidifies, pushing older crust outward in a slow-motion conveyor belt that drives the movement of continents. Where oceanic plates meet continental plates or other oceanic plates, they create deep trenches, the hadal zones where the ocean reaches its greatest depths. The Mariana Trench in the western Pacific, the deepest of these chasms, plunges to approximately 36,000 feet below sea level. If Mount Everest were placed at the bottom of the Mariana Trench, its peak would still be more than a mile underwater. These trenches form at subduction zones, where one tectonic plate slides beneath another, creating not only the trenches themselves, but also the volcanoes and earthquake zones that ring the Pacific in what geologists call the Ring of Fire. The movements are imperceptibly slow by human standards, just a few inches per year, but over geological time, they reshape the face of our planet. The ocean floor is also dotted with seamounts, underwater mountains that rise at least 3,000 feet from the seabed. Most are extinct volcanoes, formed over hotspots in Earth's mantle. Unlike land-based mountains, which are worn down by rain, wind, and ice, seamounts experience minimal erosion. As a result, some may be far older than any mountain on land, preserving a record of Earth's geological history that stretches back tens of millions of years. Some seamounts rise high enough to break the surface, forming islands. The Hawaiian archipelago represents one such chain, with each island marking the passage of the Pacific Plate over a hotspot in Earth's mantle. The oldest islands, having moved farthest from the hotspot, have been worn down and submerged again, becoming seamounts once more. This cycle creates a chronological record written in stone, revealing the history of plate movement over millions of years. Between these dramatic features lie the abyssal plains, vast flat expanses of sediment-covered seabed that rank among the flattest areas on Earth. These plains form as sediments slowly accumulate on the ocean floor, gradually burying the underlying rocky terrain. The sediments themselves tell stories of Earth's past, with each layer representing a specific period in the planet's history. Scientists can extract cores from these sediments, reading the layers like pages in a book that chronicles changes in Earth's climate, the evolution and extinction of marine species, and even the history of cosmic events. Thin layers rich in iridium, for example, mark the boundary between the Cretaceous and Paleogene periods, evidence of the asteroid impact that contributed to the extinction of non-avian dinosaurs 66 million years ago. The ocean floor also hosts more unusual features, like cold seeps where methane and hydrogen sulfide leak from the seabed, supporting specialized ecosystems similar to those found at hydrothermal vents. Brine pools, lakes of highly saline water that sit on the ocean floor, create some of the strangest environments on Earth. With salinity 3 to 8 times that of normal seawater, these pools have distinct boundaries that can be seen from submersibles, appearing like underwater lakes complete with shorelines and even waves. Perhaps the most otherworldly features of the deep ocean are its hydrothermal vent fields. These form where seawater percolates down through cracks in the ocean floor near volcanically active areas. As the water approaches magma chambers, it heats to extreme temperatures, up to 750 degrees Fahrenheit, dissolving minerals from the surrounding rock before rising back to the sea floor. When this superheated, mineral-rich water meets the near-freezing temperatures of the deep ocean, the minerals precipitate out, forming chimney-like structures that can grow at rates of up to 30 feet per year. Some of these chimneys, known as black smokers, because of the dark mineral particles they emit, can reach heights of over 160 feet. The chemistry of these vents creates some of the most extreme environments on Earth, with temperatures ranging from scalding hot to near freezing within the space of a few inches. Yet life not only survives here, it thrives, creating oases of abundance in the otherwise sparse deep sea. These vent communities have taught us that life can adapt to conditions once thought impossible, expanding our understanding of what environments might support life elsewhere in the universe. The deep ocean also serves as a vast museum of human history. Due to the cold temperatures, absence of light, and low oxygen levels in many deep-sea environments, objects that would quickly deteriorate on land or in shallow waters can remain remarkably well preserved for centuries or even millennia. Shipwrecks represent the most dramatic examples of this preservation. The wooden beams of ancient vessels, the leather of sailors' boots, even the paper of navigational charts can survive for hundreds of years in the deep sea. The RMS Titanic, resting more than 12,000 feet below the surface of the North Atlantic, still retains much of its structure and many delicate artifacts more than a century after its sinking. Even more remarkable is the preservation of organic materials. In 2009, archaeologists discovered a shipment of 4,200-year-old Egyptian beef preserved in clay pots in an ancient shipwreck near Canaan. The beef had mummified naturally in the low-oxygen environment of the deep Mediterranean, offering an unprecedented glimpse into ancient trade and culinary practices. For marine archaeologists, the deep ocean represents a treasure trove of historical information, a vast archive where the passage of time moves more slowly than on land. Each shipwreck is a time capsule, preserving not just artifacts, but entire moments in history, frozen at the instant the vessel slipped beneath the waves. Yet the deep ocean preserves more than just human history. In its sediments lies a record of Earth's past, stretching back hundreds of millions of years. By extracting and analyzing cores from the ocean floor, scientists can reconstruct ancient climates, track the evolution of marine life, and identify major events in Earth's history. Ocean sediments preserve the shells of tiny marine organisms called foraminifera, which incorporate oxygen isotopes from the surrounding water as they grow. By analyzing the ratio of these isotopes in shells of different ages, scientists can determine ocean temperatures going back millions of years, creating a detailed record of Earth's climate history. Other chemical signatures in ocean sediments reveal periods of low oxygen, changes in ocean circulation, or major extinction events. Each layer tells part of Earth's story, recording the pulse of our planet's systems over vast spans of time. The deep sea is, in many ways, Earth's most comprehensive natural archive. This archival function of the deep ocean extends to the present day, as human activities increasingly leave their mark on even the most remote environments. Pollutants like microplastics, industrial chemicals, and radioactive isotopes from nuclear testing have all been detected in deep-sea sediments and organisms, creating a stratigraphic signature of the Anthropocene, the proposed geological epoch, defined by humanity's impact on Earth systems. Despite its vastness and apparent remoteness, the deep ocean is intimately connected to the surface world and increasingly vulnerable to human activities. Commercial fishing, once limited to coastal waters, has moved progressively deeper as shallow stocks have declined. Deep-sea trawling, in which heavy nets are dragged across the seabed, can destroy ancient coral gardens and seamount communities in a single pass, devastating ecosystems that took centuries or millennia to develop. Deep-sea mining represents another frontier of human impact. The ocean floor contains valuable deposits of minerals used in electronics and renewable energy technologies. Copper, nickel, manganese, cobalt, and rare earth elements. As demand for these resources grows, so does interest in extracting them from the seabed, despite limited understanding of how such operations might affect deep-sea ecosystems. Climate change, too, reaches into the abyss. The ocean absorbs more than 90% of the excess heat generated by greenhouse gas emissions, gradually warming even its deepest layers. It also absorbs approximately 30% of the carbon dioxide released by human activities, causing ocean acidification that may particularly affect calcifying organisms like corals and certain plankton species. Yet the very vastness and mystery of the deep ocean also represent hope. In areas protected from direct human impacts, deep-sea ecosystems remain among the most pristine on Earth. Their remoteness provides a buffer, a chance to implement conservation measures before irreversible damage occurs. As we learn more about these environments, we gain not only scientific knowledge, but also a deeper appreciation for their value and vulnerability. The exploration of the deep ocean represents one of humanity's greatest remaining physical challenges. The extreme conditions, crushing pressure, near-freezing temperatures, and total darkness make it in many ways more difficult to explore than outer space. While thousands of people have climbed Mount Everest and hundreds have traveled to space, Only 3 people have reached the deepest point in the ocean, the Challenger Deep in the Mariana Trench. The first journey to the bottom took place in 1960, when Jacques Picard and Don Walsh descended in the Bathyscaphe Trieste. Their visit was brief, just 20 minutes on the bottom, and visibility was limited by sediment stirred up when they landed. It would be 52 years before another human made the journey, when filmmaker James Cameron descended in the specially designed deep-sea Challenger in 2012. Between these historic dives, exploration of the deep sea has been primarily conducted by remotely operated vehicles, ROVs, and autonomous underwater vehicles, AUVs, sophisticated robots that can withstand the extreme conditions of the deep. These technological marvels have revolutionized our understanding of the abyss, allowing scientists to observe and sample deep-sea environments without risking human lives. Modern deep-sea exploration vehicles come equipped with high-definition cameras, mechanical arms for collecting samples, and suites of sensors that can measure everything from water chemistry to current patterns. Some can stay underwater for months, mapping vast areas of seabed or monitoring deep-sea ecosystems over time. These robots have become the eyes, ears, and hands of scientists, extending human perception into a realm where our bodies cannot safely go. The challenges of deep-sea exploration go beyond just reaching the ocean floor. Communication is difficult, as radio waves don't penetrate water effectively. Most underwater vehicles rely on acoustic signals or must surface to transmit data. Power is another limitation. Batteries must supply everything from propulsion to lights to scientific instruments, and the pressure at extreme depths requires special materials and design considerations for any equipment that ventures into the abyss. Despite these challenges, the pace of deep-sea discovery has accelerated dramatically in recent decades. The development of multi-beam sonar has allowed scientists to map the seafloor in unprecedented detail. DNA sequencing technologies have revealed the genetic diversity of deep-sea life, including microorganisms that cannot be grown in laboratories, and increasingly sophisticated sampling techniques have allowed researchers to study deep-sea creatures in their natural habitat, rather than bringing them to the surface where they often die due to the dramatic change in pressure. Each advancement in technology brings new discoveries. The Census of Marine Life, a decade-long international effort completed in 2010, documented thousands of previously unknown species and highlighted how much remains to be discovered. More recent expeditions continue to find new species at a remarkable rate. In some deep-sea areas, more than half of the creatures collected may be unknown to science. What makes this ongoing exploration so important is not just the thrill of discovery, but the potential benefits to humanity. The deep ocean is a vast reservoir of genetic and chemical diversity, a library of adaptations to extreme conditions that could inspire new materials, medicines, and technologies. Researchers have already identified compounds from deep-sea organisms with promising anti-cancer, antibiotic, and anti-inflammatory properties. The enzymes of extremophile bacteria, microorganisms adapted to extreme environments, have applications in industrial processes, DNA research, and biofuel production. And the structural adaptations of deep-sea creatures have inspired innovations ranging from better body armor to more efficient underwater vehicles. Perhaps most fundamentally, studying the deep sea expands our understanding of life itself, its resilience, diversity, and capacity for adaptation. The discovery of hydrothermal vent communities revolutionized our thinking about the conditions necessary for life, suggesting that similar ecosystems might exist on other worlds with subsurface oceans, such as Europa or Enceladus. The deep sea also serves as a natural laboratory for studying evolution. In its isolated basins and trenches, species have evolved independently, adapting to local conditions and developing unique features. By comparing related species from different deep-sea environments, scientists can trace the pathways of evolution and better understand the processes that drive the diversification of life. As night deepens around you, Imagine descending through the water column, leaving the familiar world of sunlight and air far above. The pressure mounts with each foot of depth, the temperature drops, and the light fades to an endless blue twilight. Yet life persists here, transformed by the challenges of the deep, but no less vibrant for its adaptations. Bioluminescent creatures drift past like living stars, creating constellations that shift and move in 3 dimensions. Some flash briefly to startle predators, others glow steadily to attract prey or potential mates. Their light is cold, created through chemical reactions rather than heat, and often blue-green, the wavelengths that travel farthest through seawater. Deeper still, where even this bioluminescence becomes rare, life adapts in other ways. Some deep-sea creatures develop enhanced senses of touch or smell, detecting minute chemical signals or the subtle movements of water caused by distant prey. Others become highly specialized, evolving precise adaptations to exploit particular food sources or habitats. The vampire squid, despite its fearsome name, feeds primarily on marine snow, extending a long filament to capture drifting organic particles. The yeti crab cultivates gardens of bacteria on its specially adapted claws, harvesting them for food. The scaly-foot snail, found only at certain hydrothermal vents in the Indian Ocean, incorporates iron sulfide from vent fluid into its scales and shell, the only known animal to use iron in this way. Even the bacteria of the deep sea show remarkable specialization. Some have evolved to digest whale bones, breaking down fats and proteins that few other organisms can access. Others form symbiotic relationships with animals, living inside specialized organs and providing their hosts with nutrients in exchange for shelter. This specialization extends to the way deep-sea communities are structured. Unlike shallow water ecosystems, which ultimately depend on sunlight for energy, deep-sea food webs often center around chemosynthetic bacteria or the steady rain of organic matter from above. These communities may be less directly connected to surface conditions, creating a buffer against short-term changes but potentially making them more vulnerable to long-term shifts in ocean productivity or chemistry. The pace of life in the deep reflects its extreme conditions. Many deep-sea creatures grow slowly, mature late, and live extraordinarily long lives compared to their shallow water relatives. This slow life history strategy conserves energy in a food-poor environment, but also makes these species particularly vulnerable to human impacts. A deep-sea coral colony harvested in minutes may have been growing for centuries or even millennia. As we descend further into the Hadal zone, the ocean trenches that represent Earth's deepest places, even these adaptations are pushed to extremes. Pressure at these depths exceeds 16,000 pounds per square inch, enough to crush most air-filled spaces and alter the very chemistry of life. Yet specialized organisms known as Hadal fauna thrive here, pushing the boundaries of what we once thought possible for living creatures. Recent expeditions to Hadal trenches have revealed surprising diversity at these extreme depths. Rather than finding a uniform environment inhabited by a few highly specialized species, researchers have discovered distinct communities in different trenches. Some trenches appear to host unique species found nowhere else on Earth, suggesting they function as isolated evolutionary laboratories, separated from one another by shallower ridges that some deep-adapted species cannot cross. The discovery of these unique trench faunas highlights one of the most fascinating aspects of deep-sea exploration, the way it continually challenges our assumptions. Each expedition, each new technology, each careful observation reveals a world more complex, more diverse, and more interconnected than we previously imagined. In the perpetual night of the deep, far from human eyes, evolution has performed its quiet work for countless millennia, crafting strange and wonderful adaptations to an extreme environment. We are only beginning to glimpse this alien world that exists alongside our own, separated not by vast distances, but simply by the barrier of pressure and the veil of darkness. As our exploration continues, we discover not only new species, but new ecological relationships, new biochemical pathways, and new ways of understanding life itself. The deep sea reminds us that our planet still holds profound mysteries, that the frontier of discovery lies not just in distant space, but in the unexplored realms of our own world. The ocean's depths also offer perspective on humanity's place on this blue planet. From the viewpoint of the deep sea, human history is remarkably brief, a mere moment in the long, slow rhythms of Earth's systems. The oldest deep-sea corals were already ancient when the first human civilizations emerged. The layers of sediment on the ocean floor record hundreds of millions of years of Earth's history, dwarfing the timescale of human existence. Yet in our brief time on Earth, humans have influenced even these remote environments. Plastic pollution has been found in the deepest ocean trenches. Industrial chemicals and radionuclides from nuclear testing can be detected in deep-sea organisms. Fishing trawls have scarred the seabed in many regions. These impacts serve as reminders of humanity's reach and responsibility. At the same time, the deep sea offers lessons in resilience. Life in these extreme environments has persisted through multiple mass extinctions and dramatic changes in Earth's climate. The adaptations of deep-sea creatures demonstrate the remarkable flexibility of life, its capacity to find opportunity in even the most challenging circumstances. Human observations of the deep ocean span less than 2 centuries, a blink of an eye in geological time. In this brief period, we have progressed from believing the deep sea was lifeless to recognizing it as one of Earth's most extensive and unique biomes. Each year brings new discoveries, from previously unknown species to surprising ecological relationships to unexpected patterns of ocean circulation. This rapid expansion of knowledge comes at a critical time, as human activities increasingly affect even the most remote parts of our planet. Understanding the deep sea, its ecosystems, its role in global processes, and its vulnerability to human impacts has never been more important. The decisions we make in the coming decades will shape the future of this vast frontier. What makes the exploration of the deep ocean so compelling is not just its scientific significance, but the way it captures the human imagination. The deep sea embodies the essence of exploration, venturing into the unknown, facing extreme challenges, and discovering wonders beyond our expectations. It reminds us that our planet still holds magnificent secrets, waiting to be revealed by those curious and persistent enough to seek them. As you drift towards sleep, imagine the quiet darkness of the deep sea, a realm where time moves differently, where life follows unfamiliar patterns, and where the human presence is still ephemeral. In this vast wilderness beneath the waves, countless mysteries remain to be discovered, each one offering new insights into our blue planet and our place within its complex systems. The ocean holds our planet's story. In its chemistry, its sediments, its currents, and its creatures. It connects continents, regulates our climate, provides food and livelihoods for billions, and harbors more undiscovered species than any other environment on Earth. As we continue to explore its depths, we gain not only scientific knowledge, but a deeper appreciation for the remarkable world we inhabit. Tomorrow, when you wake, the ocean will still be there, covering more than 70% of our planet, containing more than 97% of Earth's water, and supporting the web of life that includes us all. Its depths will still hold mysteries, waiting for future explorers equipped with curiosity, technology, and respect for one of Earth's greatest wilderness areas. As you rest, perhaps some part of your consciousness will continue to drift through the ocean depths, moving with the slow currents that have circulated through Earth's seas for millions of years. There is a peculiar comfort in connecting with something so vast and ancient, a reminder that beyond our daily concerns flows a deeper reality, enduring, mysterious, and ultimately connected to all life on our blue planet. These currents themselves tell a story of global connection, a planetary circulation system that has helped regulate Earth's climate since the continents took their current form. Deep ocean currents move like slow rivers beneath the surface waves, carrying heat, nutrients, and dissolved gases on journeys that may span centuries. A drop of water that sinks in the North Atlantic may not resurface for 1,000 years, after traveling through the depths of all the world's major oceans. This global circulation has been called the oceanic conveyor belt, though scientists prefer the term thermohaline circulation, a name derived from the two factors that drive it: temperature, thermo, and salinity, haline. In polar regions, surface water cools and, combined with increased salinity from sea ice formation, becomes denser than the surrounding water. This dense water sinks to the ocean floor, beginning a journey that will carry it through the deep basins of the Atlantic, around Antarctica, and into the Indian and Pacific Oceans. The scale of this circulation is difficult to comprehend. Each second in the North Atlantic alone, several million cubic meters of water sink into the abyss, a flow greater than all the world's rivers combined. This cold, dense water travels along the ocean floor, eventually rising to the surface in the warmer Pacific and Indian Oceans, where it heats and becomes less dense before returning to the Atlantic. A complete circuit might take between 500 and 1,000 years, meaning that water now rising in the Pacific may have last seen the surface during the medieval period. This slow, steady pulse of the ocean moderates our climate, carrying tropical warmth toward the poles and distributing nutrients throughout the global sea. Without it, Europe would be significantly colder, and many marine ecosystems would collapse. Yet this circulation is not immutable. Evidence from ice cores and ocean sediments reveals that it has slowed or even temporarily shut down during past climate transitions, with dramatic effects on regional and global climate. In the stillness of your room, imagine these vast rivers flowing unseen beneath the ocean's surface, steady and ancient. Trillions of gallons of water moving in patterns established millions of years ago, yet vulnerable to changes in our modern world. The deep currents connect us to both the past and the future of our planet, carrying the memory of ancient climates while responding to the changes we create today. Within these currents travel not just water, but the countless drifting organisms that form the foundation of marine food webs. Plankton, a term derived from the Greek word for wanderer or drifter, encompasses a diverse community of mostly microscopic plants, animals, bacteria, and other life forms that float with the ocean's movements. Though individually tiny, collectively they outweigh all of Earth's whales, fish, and other oceanic animals combined. Phytoplankton, the plant-like members of this community, capture energy from the sun through photosynthesis, transforming it into food for themselves and ultimately for many other creatures. These microscopic organisms produce about half of Earth's oxygen. Every second breath you take comes courtesy of these ocean drifters. Their abundance and productivity vary with the seasons and ocean conditions, creating blooms that can be seen from space, vast swirls of green or turquoise spreading across the sea surface. Zooplankton, the animal component of plankton, range from single-celled protozoans to the larvae of fish and crustaceans to small but complex animals like krill. Many perform daily vertical migrations, rising toward the surface at night to feed and descending to deeper, darker waters during daylight to escape predators. This daily movement represents the largest migration of biomass on our planet, involving trillions of organisms moving through hundreds of meters of water. Some zooplankton travel much greater distances. Certain jellyfish can migrate thousands of miles, riding ocean currents to reach productive feeding grounds. Others remain in a single region but move vertically through different depth zones, adapting to changing conditions and food availability. Their translucent bodies, often glowing with bioluminescence, create living constellations in the midnight waters. As these organisms die or are consumed and excreted, their remains begin a slow descent to the ocean floor, the marine snow mentioned earlier. This gentle rain of organic material feeds the deep ocean, connecting the sunlit surface to the darkest abyss. In most of the open ocean, life in the deep depends entirely on this steady drift of food from above. The rate of this snow's descent varies with depth and particle size. Larger items, the carcasses of fish or the molted shells of crustaceans, may sink relatively quickly. Smaller particles drift more slowly, sometimes taking weeks to reach the abyssal plane. During this journey, the material is continuously processed by bacteria and zooplankton, changing its composition and nutritional value. By the time it reaches the deepest parts of the ocean, much of this material has been transformed or consumed, leaving only the most resistant components. Yet even these remnants support life in the abyss. Deep-sea holothurians, relatives of sea stars commonly known as sea cucumbers, crawl across the ocean floor, ingesting sediment and extracting the remaining nutrients. Specialized worms burrow through the mud, while crabs and other scavengers patrol for larger food items. The relationship between surface productivity and deep-sea life creates connections across vast distances. Changes in climate or ocean conditions that affect phytoplankton at the surface may impact communities on the seafloor years later, as the altered quality or quantity of marine snow makes its way to the depths. This temporal disconnect creates a kind of ecological memory in the system, where the deep ocean responds to surface conditions of the past rather than the present. In some regions, however, food arrives in the deep through more dramatic means. Submarine canyons, steep-sided valleys that cut across continental shelves and slopes, act as conduits, channeling sediment and organic material from shallow waters into the deep. During storms or underwater landslides, these canyons can experience turbidity currents, dense flows of sediment-laden water that race downslope like underwater avalanches. These turbidity currents can travel at speeds of up to 50 miles per hour, scouring the canyon walls and carrying vast amounts of material into the deep sea. They create their own distinctive features on the ocean floor, submarine fans of sediment that spread out at the canyon's mouth, similar to river deltas on land, but often much larger in scale. The largest of these submarine fans, the Bengal fan in the Indian Ocean, extends more than 3,000 kilometers from the mouth of the Ganges River, covering an area larger than Texas. Built up over millions of years by sediment carried from the Himalayas, it represents one of the largest sedimentary deposits on Earth, a monument to the power of underwater flows to shape the deep-sea landscape. These dynamic processes contrast with the apparent stillness of the deep ocean. While the abyssal plane may seem unchanging, it is constantly receiving new material from above and from the margins of continents. Over geological time, these inputs accumulate to form layers of sediment that may reach hundreds or even thousands of meters in thickness. The composition of these sediments varies with location. In areas beneath productive surface waters, they may be rich in organic matter. Closer to continents, they contain more terrestrial material, clay minerals and silt washed from the land. In the open ocean, far from land, they consist primarily of the remains of marine organisms, the shells of microscopic plankton that slowly build up as a fine ooze. Scientists can read these sedimentary layers like pages in a history book, extracting information about past climates, ocean chemistry, and biological productivity. By analyzing the species composition of microfossils or the chemical isotopes in their shells, researchers can reconstruct conditions that existed millions of years ago, long before humans began keeping records. One of the most valuable climate archives comes from foraminifera, single-celled organisms that build shells of calcium carbonate. As they grow, these shells incorporate oxygen isotopes from the surrounding water in ratios that vary with temperature. By measuring these isotope ratios in foraminifera of different ages, scientists can track how ocean temperatures have changed over time, creating a detailed record of Earth's climate history. Similar techniques allow researchers to reconstruct ancient ocean circulation patterns, productivity levels, and even the extent of polar ice caps. The ocean floor thus becomes a vast library of Earth's past, preserving information that would otherwise be lost to time. Each core of sediment brought up from the deep represents a small fragment of this planetary archive, a window into worlds and climates long vanished from the surface. The deep ocean's role as an archive extends beyond climate data. In areas where oxygen levels are low, organic materials may be preserved for extraordinary periods. Ancient shipwrecks, with their cargoes and the personal possessions of their crews, can remain intact for centuries or millennia, protected from the decay that would quickly claim them in shallower waters or on land. Even more remarkably, the remains of ancient marine life may be preserved with exceptional detail. In 2009, paleontologists discovered a 47-million-year-old fossilized whale in the Egyptian desert, a region that was once covered by a shallow sea. The fossil included not only the whale's skeleton, but also the remains of its last meal and the bacteria that had begun to consume its carcass. Such discoveries offer unprecedented insights into ancient marine ecosystems and the evolutionary history of ocean life. The deep ocean also preserves more recent human history, though not always in ways we might wish. Debris from human activities has reached even the most remote corners of the abyss. In 2019, a submersible exploring the Mariana Trench discovered a plastic bag at a depth of 36,000 feet, a sobering reminder that no part of our planet remains untouched by human influence. More deliberately placed, submarines, aircraft, and even spacecraft lie scattered across the ocean floor, relics of human conflict, accidents, or planned disposal. The ocean depths have become an unintended museum of the Anthropocene, the proposed epoch defined by humanity's impact on Earth systems. Future paleontologists studying ocean sediments from our time will find traces of plastics, heavy metals, synthetic chemicals, and radionuclides, signatures of human activity preserved in the geological record. Despite this increasing human influence, the deep ocean remains one of the least understood environments on Earth. We have better maps of the surface of Mars than of our own ocean floor. Only about 20% of the seabed has been mapped in detail, leaving vast areas essentially uncharted. Each mapping expedition reveals new features: seamounts, hydrothermal fields, cold seeps, and other structures that may host unique ecosystems. This lack of basic knowledge makes the deep ocean the ultimate frontier for biological discovery on Earth. Researchers estimate that between 1 and 2 million marine species remain undiscovered, with the majority likely residing in the deep sea. Each expedition to previously unexplored regions returns with species new to science, sometimes dozens or even hundreds from a single location. Some of these discoveries have transformed our understanding of evolution and adaptation. The colossal squid, with the largest eyes of any known animal, remained unknown to science until fragments were found in a sperm whale's stomach in the 19th century. A complete specimen wasn't captured until 2007. The ruby sea dragon, a relative of the better-known leafy and weedy sea dragons, was only discovered in 2015, hiding in plain sight among museum specimens previously misidentified as common sea dragons. Perhaps most surprising was the discovery of the Omura's whale, a 33-foot baleen whale that somehow escaped scientific documentation until 2003. That a creature so large could remain unknown in the 21st century highlights how much of the ocean remains unexplored. If a whale can hide from human knowledge, what else might be swimming in the depths? The rate of discovery suggests we have only scratched the surface of the ocean's biodiversity. In 2014, scientists using a remotely operated vehicle in the depths of the Gulf of Mexico encountered a massive school of an unknown fish species. Later identified as a new species of scad, these fish numbered in the millions, moving together in a swarm so dense it resembled an underwater cloud. How could such an abundant species have remained undocumented for so long? The answer lies partly in the challenges of deep-sea exploration. Traditional fishing methods rarely reach the depths where many of these creatures live. Even when they do, many deep-sea organisms are fragile, their bodies adapted to high pressure and cold temperatures. Brought to the surface, they often don't survive or are damaged beyond recognition. Only with the development of in situ observation technologies, submersibles, ROVs, and deep-sea camera systems have scientists been able to study many of these creatures in their natural habitat. The expense of deep-sea exploration also limits our knowledge. A single day of operation for a research vessel equipped with deep-diving technology can cost tens of thousands of dollars. Expeditions are typically brief and focused on specific research questions or locations, leaving vast areas unexamined. Despite these constraints, the pace of discovery continues to accelerate as technology improves, and more researchers turn their attention to the deep. What makes these discoveries so valuable is not just the new species themselves, but what they reveal about the potential for life to adapt to extreme conditions. The deep sea hosts some of the most unusual adaptations in the natural world, from the bioluminescent lures of anglerfish to the heat-resistant enzymes of vent bacteria to the pressure-tolerant cellular structures of hadal organisms. These adaptations have inspired innovations across multiple fields. Enzymes from deep-sea bacteria are used in cold water detergents and DNA amplification techniques. The structural properties of deep-sea sponges have informed the design of fiber optic networks and lightweight building materials. Compounds from deep-sea organisms show promise as pharmaceuticals, with anti-cancer, antibiotic, and anti-inflammatory properties. Beyond these practical applications, the study of deep-sea life expands our understanding of evolutionary processes. In isolated basins and trenches, species have evolved independently, adapting to local conditions and developing unique features. By comparing related species from different deep-sea environments, scientists can trace the pathways of evolution and better understand the processes that drive the diversification of life. The deep ocean also provides natural experiments in how ecosystems respond to extreme conditions and environmental change. At hydrothermal vents, communities must adapt to environments where temperatures can shift from near freezing to well above boiling point within inches. When vents become inactive, the organisms that depend on them must either migrate to new vent fields or perish, creating cycles of ecological succession as new vents form and old ones die out. These natural laboratories offer insights into ecological resilience and adaptation that may become increasingly relevant as Earth's climate changes. By studying how deep-sea communities respond to natural variations in temperature, chemistry, and food availability, scientists can better predict how marine ecosystems might react to human-induced changes in ocean conditions. The deep ocean also influences our planet in ways we are only beginning to understand. Its vast volume absorbs and stores heat, slowing the pace of climate change, but potentially creating a thermal debt that will affect Earth systems for centuries to come. It serves as a crucial carbon sink, removing carbon dioxide from the atmosphere and sequestering it in sediments or dissolved forms. The ocean's capacity to absorb carbon has limited the warming effect of human greenhouse gas emissions, but at a cost. As carbon dioxide dissolves in seawater, it forms carbonic acid, gradually lowering the ocean's pH in a process known as ocean acidification. This chemical change makes it more difficult for calcifying organisms, from microscopic coccolithophores to corals to mollusks, to build and maintain their calcium carbonate structures. The effects of this acidification have been observed in laboratory settings and in some surface waters, but its impact on deep-sea ecosystems remains largely unknown. Deep-sea corals, which grow extremely slowly and may live for thousands of years, could be particularly vulnerable. These corals provide habitat for numerous other species, meaning their loss could have cascading effects throughout deep-sea communities. Warming of deep waters presents another concern. While temperature changes occur more slowly in the deep sea than at the surface, they can persist for decades or centuries due to the ocean's thermal inertia. Even small temperature increases can impact organisms adapted to the normally stable conditions of the deep, potentially altering their metabolic rates, reproductive cycles, or geographic distributions. Changes in ocean circulation may also affect the distribution of oxygen in deep waters. Some regions of the ocean already contain oxygen minimum zones, areas where oxygen levels are too low to support most animal life. As the ocean warms, these zones may expand, squeezing the habitable space for many deep-sea creatures and altering the cycling of nutrients and carbon. Despite these challenges, the deep ocean also offers hope for conservation and restoration. In areas protected from direct human impacts, deep-sea ecosystems remain among the most pristine on Earth. Their remoteness provides a buffer, a chance to implement protection measures before irreversible damage occurs. Several nations have established marine protected areas that include deep-sea habitats, while international efforts are underway to create conservation frameworks for areas beyond national jurisdiction, the high seas that cover nearly half our planet. These initiatives recognize the value of the deep sea, not just for its resources, but for its biodiversity, its role in Earth systems, and its potential for scientific discovery. The deep ocean reminds us of how much remains to be learned about our home planet. Each expedition reveals new species, new ecological relationships, and new insights into the processes that shape our world. The mysteries of the abyss challenge our assumptions and expand our understanding of what is possible, both in nature and in our own innovations. As our technology improves, our exploration becomes more sophisticated. Autonomous underwater vehicles can now map the sea floor with unprecedented detail, while environmental DNA techniques allow scientists to detect species from the genetic material they leave behind in the water. New deep-diving submersibles push the boundaries of human presence in the abyss, while networks of sensors monitor deep-sea conditions over time rather than in brief snapshots. These technological advances coincide with growing recognition of the deep sea's importance. Once considered a dark, lifeless waste, the deep ocean is now understood as a critical component of Earth's biosphere, an environment teeming with life, influencing global climate, and harboring untapped knowledge about our planet's past and future. Yet even as our appreciation grows, so do the potential threats to deep-sea ecosystems. Bottom trawling, in which heavy nets are dragged across the seabed, can destroy ancient coral gardens and seamount communities in a single pass. Mining interests are increasingly looking to the deep sea as a source of valuable minerals, while climate change gradually alters the chemistry and circulation of the deep ocean. The challenge for our generation is to balance exploration and potential exploitation with conservation, to learn about the deep sea without irreparably damaging its delicate ecosystems. This requires not just scientific research, but also thoughtful policy, international cooperation, and a long-term perspective that considers the value of these environments beyond immediate economic benefit. For most of human history, the deep ocean existed beyond our reach and largely outside our awareness. Now, as technology brings it within our grasp, we have the opportunity, and perhaps the obligation, to approach it with wonder, respect, and humility. The decisions we make in the coming decades will shape the future of Earth's last great wilderness, determining whether it remains a frontier of discovery or becomes merely another resource to be consumed. As you drift towards sleep, imagine again the silent darkness of the deep, a realm where time moves differently, where life follows unfamiliar patterns, and where our understanding is still in its infancy. In this vast wilderness beneath the waves, countless mysteries await discovery, each one offering new insights into our blue planet and our place within its complex systems. The darkness of the deep is not empty, but filled with life and light of its own making. Bioluminescence, the biological production of light, is remarkably common in the deep sea, where an estimated 90% of creatures can produce some form of glow. Unlike the harsh glare of artificial light, this living radiance comes in soft blues and greens, brief flashes and steady glows, each serving a specific purpose in the lightless world. Some species use light to hunt, dangling glowing lures to attract prey or illuminating the water to spot potential meals. Others use it defensively, startling predators with sudden flashes or using light to disguise their silhouettes against the faint glow from the surface. Many use bioluminescence to communicate, creating patterns that help them identify members of their own species or attract mates in the vastness of the deep. The chemistry behind this light is elegant and efficient. It involves a compound called luciferin that, when oxidized by the enzyme luciferase, releases energy in the form of light rather than heat. This cold light represents one of evolution's most beautiful solutions to the challenge of life in darkness, a way to communicate, navigate, and hunt without wasting precious energy as heat. Scientists have harnessed these bioluminescent systems for research, using luciferase as a marker to track biological processes or detect specific compounds. The green fluorescent protein, first isolated from a bioluminescent jellyfish, has become an invaluable tool in biomedical research, earning its discoverers a Nobel Prize in 2008. Once again, the deep ocean has provided inspiration and tools for human innovation. Beyond bioluminescence, deep-sea creatures have evolved other remarkable adaptations to their extreme environment. Many fish have specialized pressure-sensing organs called lateral lines that detect the subtle movements of water caused by other creatures or obstacles. Some have developed enhanced senses of smell, capable of detecting minute concentrations of chemicals that might indicate food or danger. Vision, too, has evolved in fascinating ways. Many deep-sea fish have enormously expanded eyes, sometimes taking up half their headspace, to capture what little light exists. The barrelly fish has tubular eyes that point upward, searching for the silhouettes of prey against the faint glow from the surface. Protected by a transparent dome filled with fluid, these eyes can rotate to look forward as well, giving the fish a versatile visual system despite the near darkness of its environment. Other species have entirely abandoned vision. The blind cusk eel, found in ocean trenches, has lost its eyes through evolution, relying instead on other senses to navigate and find food. In the cave systems of ankyloline pools, landlocked bodies of water with connections to the ocean, blind shrimp and fish have evolved independently, their eyes reduced to vestigial structures in environments where vision offers no advantage. Perhaps the most extreme adaptations are found in creatures that live near hydrothermal vents, where the water can reach temperatures above 750 degrees Fahrenheit. The Pompeii worm constructs tubes near these vents, with its head in cool water and its tail near the scorching heat of the vent fluid. Its back is covered with bacteria that may help insulate it from the extreme temperature gradient it experiences, one of the most dramatic temperature ranges tolerated by any animal. Even more remarkable are the microorganisms that live within the vent fluid itself, extremophiles that thrive in conditions once thought incompatible with life. Some can survive temperatures above 250 degrees Fahrenheit, while others live in highly acidic or alkaline environments or withstand radiation levels that would kill most organisms. These extremophiles have expanded our understanding of the conditions under which life can exist, with implications for both Earth's history and the search for life on other worlds. The adaptability of life in the deep challenges our assumptions about what is possible. Each strange feature, each unexpected capability represents a solution to the unique challenges of this extreme environment. The deep ocean has been a laboratory for evolution for millions of years, producing innovations that human technology is only beginning to understand and emulate. This evolutionary creativity extends beyond individual adaptations to the complex relationships between species. In environments where food is scarce and encounters are rare, organisms have developed intricate symbioses, partnerships that allow them to survive where either species alone might fail. At hydrothermal vents, tube worms with no mouth or digestive system host chemosynthetic bacteria within specialized organs. The bacteria convert chemicals from the vent fluid into food, which they share with their host in exchange for a stable, protected environment. Similar relationships exist between mussels, clams, and various microorganisms, creating networks of interdependence that support the extraordinary productivity of vent communities. Even more unexpected are the relationships found in the open ocean. Certain deep-sea anglerfish females host bioluminescent bacteria in their lures, creating the glow that attracts prey. The bacteria receive a steady supply of nutrients from their host, while the fish gains a living light that requires no energy to maintain, a partnership of mutual benefit in the darkness of the deep. These symbioses highlight the interconnectedness of life, even in environments that might seem isolated or extreme. They remind us that survival often depends not on competition alone, but on cooperation and mutual adaptation. In the harsh conditions of the deep, evolution has repeatedly favored relationships that allow organisms to share resources, divide tasks, and overcome challenges together. The deep sea also hosts some of the most unusual reproductive strategies in the animal kingdom. In an environment where finding a mate can be extraordinarily difficult, organisms have evolved creative solutions to ensure the continuation of their species. Many deep-sea creatures are simultaneous hermaphrodites, possessing both male and female reproductive organs. This adaptation allows any two adults of the species to mate when they encounter one another, doubling the potential reproductive opportunities in an environment where meetings are rare. Others practice sequential hermaphroditism, changing sex at some point in their lives, often in response to social or environmental cues. The male anglerfish takes this reproductive flexibility to an extreme. In many species, the tiny male permanently fuses to the female, becoming essentially a parasite that provides sperm when needed. His eyes, fins, and most of his internal organs degenerate, while his circulatory system connects to the females. Multiple males may attach to a single female, ensuring she has a constant supply of sperm without the need to find new mates. A dramatic solution to the challenge of reproduction in the vastness of the deep. Other species have evolved elaborate courtship displays visible in the darkness. The male ostracod crustacean, barely the size of a sesame seed, can create complex patterns of blue light, secreting chemicals into the water that react to form a glowing trail. Each species has its own distinctive light pattern, allowing females to identify appropriate mates even in the dark. The precision and beauty of these displays rival any courtship ritual in more familiar environments. Some deep-sea organisms bypass the challenge of finding mates through asexual reproduction. Certain sea anemones can split in two, each half growing into a complete individual. Others produce genetically identical larvae that settle nearby, creating large single-species communities from a single founding individual. These strategies allow species to establish populations in isolated locations, where sexual reproduction might be impossible due to low population density. The diversity of reproductive adaptations in the deep sea reflects both the challenges and opportunities of this environment. The same conditions that make finding a mate difficult, vast spaces, sparse populations, perpetual darkness, have driven the evolution of creative solutions, from physiological changes to behavioral adaptations to entirely new reproductive systems. This evolutionary creativity is not limited to reproduction. Deep-sea creatures have developed equally diverse strategies for feeding, defense, movement, and energy conservation. The gulper eel can expand its jaw and stomach to consume prey larger than itself. The vampire squid wraps itself in a webbed cloak, becoming nearly invisible in the darkness. The deep-sea hatchetfish has evolved a body so thin it virtually disappears when viewed from the side, while its ventral surface is covered with light-producing organs that match the faint illumination from above, making it invisible from below. A strategy called counter-illumination. In environments where food is scarce, many organisms have evolved to be opportunistic feeders, capable of consuming whatever edible material they encounter. The hagfish, an ancient jawless fish found on the ocean floor, can absorb nutrients directly through its skin as well as through its mouth. It can survive months without feeding and can tie itself in a knot to gain leverage when tearing chunks from large food items. An unexpectedly sophisticated behavior for a creature that has remained largely unchanged for 300 million years. Other deep-sea creatures have specialized in extreme efficiency. The barrelly fish's transparent head allows it to keep its sensitive eyes protected while looking in any direction for food. The stoplight loose-jaw dragonfish produces red light, invisible to most deep-sea creatures, to illuminate prey without alerting them to its presence. The black swallower's expandable stomach allows it to take advantage of rare encounters with larger fish, storing energy for the long intervals between meals. These adaptations, honed over millions of years, represent not just solutions to the challenges of the deep, but potential models for human innovation. Engineers have studied the pressure-resistant structures of deep-sea organisms to improve the design of submarines and diving equipment. Materials scientists have examined the properties of sponge skeletons for inspiration in creating stronger, lighter building materials. Medical researchers have investigated compounds from deep-sea bacteria and fungi for potential pharmaceutical applications. The deep ocean thus serves as both a natural laboratory and a library of innovations, a reservoir of biological and chemical diversity with untapped potential for human benefit. Yet our knowledge of this diversity remains incomplete, with new species and compounds discovered on nearly every expedition to unexplored regions of the deep. This ongoing discovery highlights one of the paradoxes of modern marine science. At a time when human activities increasingly affect even the deepest parts of the ocean, our understanding of these environments remains fragmentary. We are changing ecosystems before fully documenting their components or understanding their functions. We are extracting resources without comprehending the long-term consequences for deep-sea biodiversity or global ocean processes. The pace of human impact has accelerated in recent decades. Deep-sea fishing fleets now target species that live thousands of feet below the surface, capturing not only commercial species, but also the bycatch of other organisms that may take decades to recover due to their slow growth rates and delayed maturity. Bottom trawling, described by some marine scientists as the underwater equivalent of clear-cutting a forest, can destroy deep-sea coral gardens and sponge grounds that have grown over centuries or millennia. Interest in deep-sea mining has grown as demand increases for the minerals used in electronics and renewable energy technologies. The ocean floor contains valuable deposits of copper, nickel, manganese, cobalt, and rare earth elements, both in the form of polymetallic nodules, rocky concretions that lie on the abyssal plain, and in mineral-rich crusts on seamounts. Several companies and countries are developing technologies to extract these resources, despite limited understanding of how such operations might affect deep-sea ecosystems. Even the deep ocean's remoteness no longer protects it from broader environmental changes. Plastic pollution has been found in the deepest ocean trenches, carried there by currents or sinking with marine snow. Persistent organic pollutants, industrial chemicals that resist degradation, accumulate in deep-sea organisms just as they do in more familiar wildlife. Climate change gradually alters the temperature, chemistry, and circulation of the deep ocean, with potentially far-reaching consequences for its ecosystems. These threats emerge at a time when we are only beginning to appreciate the deep sea's importance, not just for its resources or biodiversity, but for the essential services it provides. The deep ocean helps regulate our climate, cycling carbon and heat through its vast volume. It supports fisheries that provide protein for billions of people. It maintains ecological processes that keep marine ecosystems healthy and productive. And it holds answers to fundamental questions about life on Earth and potentially elsewhere in the universe. Balancing the use and protection of the deep sea represents one of the great challenges of our time. It requires not just scientific research, but also thoughtful policy, international cooperation, and a long-term perspective that considers the value of these environments beyond immediate economic benefit. The decisions we make in the coming decades will shape the future of Earth's last great wilderness, determining whether it remains a frontier of discovery or becomes merely another resource to be consumed. As our technology improves, our exploration becomes more sophisticated. Autonomous underwater vehicles can now map the sea floor with unprecedented detail, While environmental DNA techniques allow scientists to detect species from the genetic material they leave behind in the water, new deep-diving submersibles push the boundaries of human presence in the abyss, while networks of sensors monitor deep-sea conditions over time rather than in brief snapshots. These technological advances coincide with growing recognition of the deep sea's importance. Once considered a dark, lifeless waste suitable only for dumping unwanted materials, the deep ocean is now understood as a critical component of Earth's biosphere, an environment teeming with life, influencing global climate, and harboring untapped knowledge about our planet's past and future. The challenge lies in translating this growing appreciation into effective protection. The deep sea spans national boundaries and includes vast areas beyond any country's jurisdiction, the high seas that cover nearly half our planet. Governing these shared spaces requires international cooperation and frameworks that balance multiple interests while safeguarding the ocean's long-term health. Progress has been made in recent years. Several nations have established marine protected areas that include deep-sea habitats, while discussions continue at the United Nations regarding a treaty to conserve biodiversity in areas beyond national jurisdiction. Scientific organizations have developed guidelines for responsible research in the deep sea, and some commercial interests have committed to voluntary moratoriums on activities in ecologically sensitive areas. Yet significant challenges remain. Our knowledge of deep-sea ecosystems is still limited, making it difficult to predict the impacts of human activities or design effective protection measures. The remoteness of the deep ocean complicates monitoring and enforcement, while the high costs of deep-sea research limit our ability to gather the information needed for sound management decisions. Perhaps most fundamentally, we face a challenge of values and perspective. The deep sea operates on timescales far longer than human planning horizons. Deep-sea corals may grow only millimeters per year, taking centuries to reach maturity. Seamount communities develop over thousands of years. The ocean circulation that regulates our climate completes a cycle over half a millennium or more. In contrast, economic and political decisions typically focus on much shorter timeframes: quarterly profits, election cycles, 5-year plans. Bridging this gap requires a shift in thinking, a willingness to consider the consequences of our actions not just for our own generation, but for those that will follow us. It asks us to value not just what the ocean can provide today, but what it might offer in centuries to come, both material resources and less tangible benefits like knowledge, inspiration, and the simple wonder of a world still wild and mysterious. The deep sea challenges us to expand our circle of concern beyond familiar environments and organisms. Its creatures may seem alien or distant from our daily experience, yet they are part of the same planetary system that supports all life on Earth. The health of the deep ocean affects the health of the entire marine environment, which in turn influences our climate, food supply, and even the air we breathe. As you rest, perhaps you might imagine the slow, patient processes unfolding in the darkness far below the ocean's surface. The gentle drift of marine snow through the water column, the gradual growth of deep-sea corals, adding millimeters each year to structures that may have begun growing before the founding of Rome, the circulation of water through the global ocean, carrying the memory of surface conditions from centuries past. There is a profound tranquility in these processes, a reminder that beneath the rapid pace and constant changes of human society flows a deeper rhythm, the steady pulse of natural systems that have operated for millions of years. This continuity offers a different perspective on our place in time, connecting us to both the ancient past and the distant future through the medium of the ever-flowing ocean. The deep sea also reminds us of the limits of human knowledge and the boundless potential for discovery. Despite centuries of exploration and rapid technological advancement, we have directly observed less than 1% of the deep ocean floor. Each expedition reveals new species, new ecological relationships, and new insights into the processes that shape our world. This continuing discovery differentiates the deep sea from other frontiers. While we have mapped the entire surface of the Moon and Mars in higher resolution than much of our ocean floor, these extraterrestrial environments offer less biological diversity than a single hydrothermal vent field. The deep ocean represents not just a physical frontier, but a biological and ecological one, a realm where life has evolved in directions we are only beginning to understand. The mystery of the deep connects us to a fundamental human experience, the wonder of encountering the unknown. Since our earliest ancestors first ventured onto the open water, the ocean has symbolized both opportunity and uncertainty. Ancient maps marked unexplored seas with warnings or fantastic creatures, expressing both fear of the unknown and fascination with what might lie beyond the horizon. Today we approach the deep ocean with more sophisticated tools, but the same essential curiosity. What lives in the Hadal trenches we have barely begun to explore? What chemical compounds might deep-sea organisms produce that could benefit human health or technology? How do deep-sea communities respond to changes in their environment? And what might they teach us about resilience and adaptation? These questions matter not just for their scientific interest, but for their potential to expand our understanding of life itself, its diversity, its adaptability, and perhaps even its origins. The discovery of hydrothermal vent communities in 1977 revolutionized our thinking about where and how life might exist. Before this finding, scientists had assumed that all ecosystems ultimately depended on photosynthesis and the sun's energy. The revelation that entire communities could thrive on chemical energy from Earth's interior opened new possibilities for the conditions under which life might emerge, both on our own planet and potentially elsewhere in the universe. Similar revelations may await us in the deep ocean. Each new discovery has the potential to challenge our assumptions and extend our understanding of what is possible. The deep sea reminds us that our knowledge is always incomplete, that nature's creativity exceeds our expectations, and that the journey of scientific discovery is endless. As this journey continues, it benefits from the integration of traditional knowledge with modern scientific approaches. Indigenous peoples in coastal regions around the world have accumulated detailed understanding of marine environments through centuries of observation and interaction. This knowledge, passed down through generations, often includes information about deep-sea creatures that occasionally appear at the surface or wash ashore after storms. In Hawaii, traditional stories describe the hunting behavior of deep-sea squid that scientists have only recently been able to observe directly. Pacific Island navigators have long used knowledge of deep-water currents to guide their voyages across thousands of miles of open ocean. Aboriginal Australians preserve memories of sea level changes that flooded coastal plains at the end of the last ice age, events confirmed by modern geological research. By recognizing the value of diverse knowledge systems, marine scientists enrich their understanding of the ocean and establish more meaningful connections with coastal communities. This collaborative approach becomes increasingly important as decisions about ocean management affect not just scientific or commercial interests, but also the cultural practices and livelihoods of people who have maintained relationships with marine environments for countless generations. The deep sea thus connects us not only to natural history, but to human history as well. It preserves artifacts from ancient trade routes and testimony to more recent conflicts. It holds evidence of how people have interacted with the ocean over millennia, from the earliest coastal settlements to modern global commerce. And it continues to influence human experience, shaping weather patterns, supporting fisheries, and inspiring art, literature, and imagination. As we drift toward the end of our journey through the ocean depths, it's worth considering what the future might hold for our relationship with this vast frontier. We stand at a pivotal moment, a time when human activities increasingly affect even the most remote parts of the ocean, yet also a time of unprecedented opportunity to explore, understand, and protect these environments. New technologies continue to expand our capabilities for deep-sea research. Autonomous underwater vehicles grow more sophisticated, able to navigate complex terrain and operate for extended periods without human control. Advanced sensors can detect subtle changes in water chemistry, temperature, or biological activity, building a more comprehensive picture of deep-sea conditions. Genetic techniques allow scientists to identify species from environmental DNA, recognizing the presence of organisms without having to capture them directly. These innovations promise to accelerate the pace of discovery, revealing more of the deep ocean's secrets and monitoring its changing conditions. They may help us identify areas of particular ecological importance, track the impacts of climate change, and develop more effective conservation strategies. They might even allow us to explore environments that have remained inaccessible due to extreme depth, temperature, or other challenges. At the same time, growing awareness of the ocean's importance has sparked new initiatives for research, conservation, and sustainable management. The United Nations Decade of Ocean Science for Sustainable Development, running from 2021 to 2030, aims to expand knowledge of the ocean and ensure this knowledge informs policy decisions. Various international agreements seek to protect vulnerable marine ecosystems, reduce pollution, and establish a framework for managing activities in areas beyond national jurisdiction. Individual actions also contribute to this changing relationship. As consumers become more aware of their connection to the ocean, many choose seafood from sustainable sources, reduce their use of single-use plastics, or support organizations working to protect marine environments. Educators incorporate ocean literacy into curricula, helping students understand not just the scientific facts about the ocean, but their own role in its future. These efforts reflect a gradual shift in how we value the ocean, a movement from seeing it primarily as a resource to be extracted or a waste repository to recognizing it as a complex system that sustains life on Earth, including human life. This shift doesn't require abandoning the use of ocean resources, but rather approaching that use with greater knowledge, care, and foresight. The deep ocean, once perceived as a dark and lifeless void, now appears as a vast and vibrant frontier, a place of extraordinary biodiversity, geological wonders, and untapped knowledge. Its exploration connects us to the thrill of discovery, the humility of encountering the unknown, and the responsibility of protecting what we have only begun to understand. As you rest, perhaps you'll carry some small awareness of this hidden realm that covers so much of our planet. Beyond the familiar shoreline, beneath the surface waves, past the twilight zone where sunlight fades, stretches a world we are only beginning to comprehend. Its currents circulate through global systems that regulate our climate. Its creatures demonstrate the remarkable adaptability of life. Its sediments preserve the history of our planet, while its unexplored regions promise future discoveries we cannot yet imagine. The ocean connects us all, not just to each other across continents and cultures, but to the deep past and the distant future of our blue planet. It reminds us that beyond our daily concerns flows a deeper reality, enduring, mysterious, and ultimately connected to all life on Earth. As sleep approaches, imagine once more those gentle currents flowing through the abyss, carrying the memory of ancient climates and the promise of discoveries yet to come. The slow growth of deep-sea corals, adding millimeters each year to structures that may outlast our own civilization. The quiet drift of creatures through the darkness, each adapted in its own way to one of the most extreme environments on our planet. There is peace in connecting to something larger and older than ourselves, a system that has endured for billions of years and will continue long after we are gone. The ocean's depths hold not just scientific knowledge, but a kind of wisdom. The patient, persistent creativity of evolution, the resilience of life in the face of extraordinary challenges, the interconnectedness of systems that span our entire world. As your consciousness begins to drift like those deep ocean currents, perhaps some part of you will continue exploring the mysteries that lie beneath the waves. Or perhaps you'll simply rest, cradled in the knowledge that beyond our human world of light and air exists another reality. Vast, ancient, and filled with wonders we are only beginning to comprehend. Either way, the deep ocean remains, flowing through the night, connecting past to future through its eternal waters. May your sleep be as peaceful as the abyssal plain, as deep as the ocean trenches, and as full of gentle wonders as the world we've explored tonight. Good night, and may your dreams carry you to new frontiers, both within and beyond our blue planet's embrace.